Wave theory, problems on normal incidence of a plane wave over the plane surface of a conductor. Series on electromagnetic field theory, lecture number 4.46. When a plane wave, falls normally over a plane conductor surface, it gets reflected without any transmitted or refracted wave. The reason is, inside a conductor, field cannot exist and hence wave cannot exist. So in the present situation of wave incidence over the conductor surface, only reflected wave exists. Of course, this reflection process, this reflection phenomena obeys Snell's laws. In the present session, the focus is on problems set around normal incidence of a plane wave over the plane surface of a conductor. To begin with, we consider a problem example 1. A 30 MHz plane wave with field intensity E equal to 120 pi volts per meter traveling in a medium with epsilon r equal to 2.25 is falling normally over a thick copper sheet. Sigma equal to 6 into 10 power 7 moles per meter. This is conductivity. Determine the amplitude and location of first node and antinode for E and H. Before going to the solution process, we need to recollect the fact that when wave falls over the surface of a conductor, reflection happens obeying Snell's laws. When the incidence is normal, reflection is also normal. Now, there are two waves, normal to the reflecting surface, traveling in opposite directions, incident wave and reflected wave. Interference between them results in standing wave pattern. Standing wave pattern means formation of nodes and antinodes. Nodes and antinodes for electric field, nodes and antinodes for magnetic field too. Node for electric field happens right over the surface, reflecting surface, and antinode for H forms right at the reflecting surface. At a distance of lambda by 4 from node, antinode, from antinode, node happens for both electric and magnetic fields. With this understanding, with this information, let us move to find the solution to the problem. Normal incidence leads to normal reflection. Interference between incident and reflected waves gives rise to standing wave pattern in front of the copper sheet. Given that in the incident wave electric field amplitude is E is 120 pi volts per meter, but E by H is, in the plane wave, E by H is eta. Eta is 120 pi by root epsilon r. Epsilon r is 2.25. So E by H in the present case is 80 pi ohms. Therefore, magnetic field is E by H is 80 pi. Therefore, H is E by 80 pi. It is 1.5 amperes per meter. Now, let us consider E field in front of the reflecting surface. First node where amplitude is 0 occurs right over the surface. First antinode where amplitude is twice that of the incident wave equal to 2 into 120 pi equal to 240 pi volts per meter occurs at a distance of lambda by 4, that is 1.67 meters from the surface. For H field, first antinode where amplitude is twice that of incident wave equal to 2 into 1.5, 3 amperes per meter occurs right over the surface. First node where amplitude is 0 occurs at a distance of lambda by 4. Note the distance between first node of E and first node of H is lambda by 4. In the above wavelength lambda by 4, we have calculated how this lambda has come into being from frequency. Lambda is V by F, velocity by frequency. Velocity is C by root epsilon r. From that we got lambda as 6.67. Another problem, example 2. A 300 MHz plane wave with field intensity E equal to 2 volts per meter traveling in free space is falling normally over thick copper sheet. Conductivity is given by this formula. Find A. Electric field intensity E and magnetic field intensity H at the plane surface, and B. The field intensities at distances of lambda by 4, lambda by 2 normal to the surface, and also the reflection quotient and surface current density. As incidence is normal, reflection is also normal. This is known to us. It is from Snell's laws. Angle of incidence is equal to angle of reflection. And interference between them leads to standing wave pattern in front of the copper sheet. Given in the incident wave, the electric field E is 2 volts. E by H is 120 pi eta. So therefore H is E by 120 pi. It becomes 1 by 60 pi amperes per meter. At the surface, electric field is 0 because node formation. As the electric vector on normal incidence undergoes complete phase reversal, forming node. At node, field is 0. However, the magnetic vector gets reflected without any phase reversal. So superposition between them happens in a positive direction. So amplitude becomes double. So H equal to 2 by 60 pi. It is 1 by 30 pi amperes per meter. B. In the resultant standing wave pattern, node for electric field and anti-node for magnetic field exists right at the surface at a distance of lambda by 4. Anti-node for electric field and node for magnetic field, and at a distance of lambda by 2, node for electric field and anti-node for magnetic field occurs. This is from properties of standing wave pattern. Reflection quotient value is C. From C, reflection quotient value is always -1 when the incidence is normal on perfect conductor irrespective of field intensity or frequency. This is -1. Surface current density. See, when wave falls over a conductor, certain currents flow over the surface. So the current density, surface current density of those currents, K, is equal to H. T. Here T stands for tangential component of magnetic field that is there in the incident wave. It is therefore 1 by 30 pi amperes per incidence plus reflected. HT means tangential component of the magnetic field that exists at the surface. At the surface there exists incidence plus reflected too. So 1 by 60 plus 1 by 60. Their antinode formation, therefore it becomes 1 by 30 pi amperes per meter. The electric field strength of a 300 megahertz plane wave in free space is 1.5 volts per meter. When it falls over a thick copper plate, normally determine electric field strength at the surface, magnetic field strength at the plate face, surface current density. For copper, assume epsilon equal to epsilon naught, mu equal to mu naught, and sigma is 5.8 into 10 power 7 Siemens per meter. Note, if the conductor is a perfect conductor, conductivity tending to infinity, then electric field strength at the surface is naturally 0 because node formation takes place. Magnetic field strength, anti-node formation takes place. Magnetic field strength can be computed. It is non-zero. But here, it is not perfect conductor. It is a good conductor. Copper is a good conductor. This is practical case. So answer for A cannot be 0. So how to find out electric field strength? The process is this. Before going to the actual solution, let us compute eta to intrinsic impedance of the copper. Intrinsic impedance is given by square root j omega mu by sigma plus j omega epsilon, but sigma is very large, so j omega epsilon can be neglected. J omega is available, mu is available, sigma is given, everything is given here. So one can calculate, it comes out to be 6.39 at an angle of 0.785 radians milliohms. This is intrinsic impedance of copper. Now let us move to find answer for part A. As incidence is normal, electric field is tangential to surface. From E tan continuity boundary condition, field strength over the surface is equal to that just inside the plate. Transmitted field, which is a product of transmission quotient with incidence field. Incident field is given as 1.5 volts. EI is 1.5. Now, if you multiply this 1.5 with the transmission quotient, we know the field just inside the surface boundary in the conductor. E tan is continuous, so outside field is same as inside field. So this outside field now is EI multiplied by transmission quotient. Transmission quotient is 1 plus reflection quotient. 1 plus reflection quotient means it comes out to 2 eta 2 by eta 2 plus eta 1. This is transmission quotient. We know eta 2 we have already calculated. Eta 1 is free space means 377 ohms. Substitution and all that gives us ET, that is field just over the surface outside, 50.85 at an angle of 45 degrees microvolts per meter. Now B, inside plate just below surface, electric to magnetic field strength ratio is eta 2, and hence magnetic field strength at plate surface is ET by inside plate. This is inside plate. ET by eta 2 HT. HT is ET by eta 2. ET is known, eta 2 is known, so HT is 7.96 milliamperes per meter. Surface current density is equal to tangential magnetic field, and hence it is K is H tan, HT is already calculated 7.96 milliamperes. Power loss per square meter, it is a case effective square, RMS value square multiplied by RS. K is available here. So RS, in the above, RS is found from real part of intrinsic impedance of the copper. We have already determined intrinsic impedance of the copper. Real part is RS. So using that one can, this 1 by root is to find effective value, RMS value. This is amplitude. K is amplitude. 7.96 is amplitude. Another problem, example 4. The electric field strength of a 3 GHz plane wave in free space is 5 volts per meter. When it falls for a thick copper plate, normally determine depth of penetration, electric field strength at the surface, conduction current density at the surface, conduction current density at a distance of 0.01 millimeter below the surface impedance. For copper, assume epsilon equal to epsilon naught, mu equal to mu naught, sigma is 5.8 into 10 power 7 Siemens per meter. So depth of penetration, electric field strength at the surface, etc., etc. Now, before going to the actual solution process, let us calculate eta 2, that is intrinsic impedance of the copper. It is 20.21 at an angle of 0.785 milliohms. Depth of penetration or skin depth formula, this is standard formula. Given data can be substituted to find it equal to 1.21 micrometers. Electric field strength at the surface. In the previous problem, we calculated same quantity, of course for different data, but the process is same. This is transmission quotient. This is incident wave electric field. Eta is 536 at an angle of 0.785 microvolts per meter. Conduction current density at the surface. It is a standard formula, Ohm's law in point form. J naught is conductivity, electric field intensity becomes equal to 31.10 kiloamperes per meter square. D, attenuation constant is inverse of skin depth. We have already computed skin depth. Inverse it, we will be getting 0.826 into 10 power 6 nepers per meter. Here one point to note is attenuation constant is very high, 10 power 6. It implies wave cannot travel much distance in a conductor. Current density at a depth Z equal to 0.01 millimeter below the surface can be found as using this relation. Amplitude falls exponentially. So that fact is expressed in the form of this relation. Ultimately we get J equal to 8.04 ampere per meter square. Here it is assumed that wave travel is along positive Z direction. For conductors, surface impedance is equal to intrinsic impedance. Intrinsic impedance we have already calculated, available with us, that is equal to surface impedance. Another problem, determine reflection coefficient when 1 MHz wave traveling in free space falls normally over a thick copper sheet, steel sheet. So data pertaining to copper is that data are given, data pertaining to steel sheet are also given. We use this data. A, copper, B, steel. Copper, using given values, intrinsic impedance of the copper can be found without much difficulty. It is equal to 369 at an angle of 0.785 micro ohms. Reflection quotient for copper with this just found eta with eta 1. Eta 1 means free space intrinsic impedance. It is 377 ohms. Using these two quantities, one can find reflection quotient. Eta 2 minus eta 1 by eta 2 plus eta 1. It comes out to be minus 0.99 at an angle of 1.39 into 10 power minus 4 degrees. Steel. Using the given values, the intrinsic impedance of steel can be found. So eta first, then the reflection quotient. Here one point of clarity. If the sheet is made with a perfect conductor sheet. Reflection quotient is always -1, but the sheet is not a perfect conductor. In case A, it is made with copper, good conductor, not perfect conductor. In case B, it is made with steel, a good conductor maybe, but not perfect conductor. So, reflection quotient. Even in this case also, notice it is near to -1. In both the cases, it is near to -1, but not, of course, not -1. -1 happens only in case of perfect conductors. This is what I want to share with you regarding normal incidence of a plane wave over the plane surface of a conductor.